All right, we're about to jump into a concept that is absolutely central to mechanics, but it's one of those things that can be a little tricky at first. We're talking about the moment of a couple. Now, it sounds complicated, but it's really just an invisible force of pure rotation. And trust me, once you get it, you're going to start seeing it absolutely everywhere. So, to kick things off, let me ask you this. What do these three things have in common? You've got a steering wheel, a regular old water valve from the side of a house, and a lug wrench for changing a flat tire. They look totally different, right? But they all work using the exact same mechanical principle. And that principle is the moment of a couple. To really get a feel for this, let's just focus on the one we all know best. We're going to call this the steering wheel effect. Think about it. When you turn a steering wheel, what are your hands actually doing? You're applying two separate forces, aren't you? One hand is pushing up and away from you, and the other is pulling down and towards you. The forces are equal, but they're going in opposite directions. And here's the key. You're not actually pushing the whole steering column forwards or backwards. There's no net push or pull. The only thing that happens is a perfect, pure twist. Okay, so this steering wheel effect isn't just a random name I made up. It has a real, formal name in engineering and physics. So let's get into the official definition. And there you have it, a couple. It's just two forces that are parallel. They have to have the same strength, the same magnitude, but they're pointed in opposite directions. Because that push-up is perfectly canceled out by the pull-down, the total force on the object is zero. There's no overall push. The only thing that's left is that tendency to spin. And that's the whole magic of a couple. You know, this slide really gets to the heart of what makes a couple so special. If you just apply a single force to something, like if you push a box across the floor, it translates. It moves from one spot to another. But a couple is different. It's perfectly balanced so that it only creates rotation. It's really the difference between shoving something and just spinning it in place. So now we get to what is probably the most important, and maybe the most, well, kind of mind-bending property of a couple. It's a characteristic that's so unique you can almost think of it as its own little superpower in the world of physics. Let's head back to our steering wheel for a second. Okay. Picture your hands in the classic 9 and 3 o'clock positions. You do the push-pull thing and the wheel turns. You feel that turn, right? Okay, now for part 2 of this little thought experiment. Keep the amount of twisting effort exactly the same, but just move your hands. Put them at the top and bottom at the 12 and 6 o'clock spots. You're still applying that same equal and opposite push and pull. So what happens to the car? Exactly nothing different happens. The car turns just the same. And this is what's so incredible. The turning effect, that moment of the couple, it doesn't care where on the wheel you apply it. It isn't tied down to one spot. This is what we call a free vector, and that's a total game changer because it means that rotational effect can be moved anywhere on the object and the result is the same. That freedom is what lets engineers simplify incredibly complex problems. So, if this turning effect is the same no matter where we apply it, how do we actually measure it? How do we put a number on it and figure out which way it's twisting? Well, there are two main ways to do it. The scalar way is the easiest one to wrap your head around. M equals F times D. You just take the strength of one of those forces, F, and multiply it by the perpendicular distance between them, D. That gives you the raw power of the twist. But for the full picture, especially in 3D, we use the vector cross product. This formula doesn't just give us the magnitude, it also tells us the exact axis that the object is rotating around, which, as you might remember, you can figure out using the good old right-hand rule. Okay, this all might seem like a really neat idea in a textbook, but its real power, its real value, is in how it's used. So let's take a look at how engineers actually put couples to work. The real world is messy. I mean, think about a bridge, or an airplane wing, or even a robotic arm. They're all being pushed and pulled on by tons of different forces all at once. And this is where that free vector superpower we were just talking about becomes this incredibly powerful tool for engineers, because it lets them make sense of all that chaos. So here's the trick. Let's say you've got a force hitting an object at point A, but for your analysis, you really need to understand its effect over at point B. Well, you can't just pick up the force and move it. That would change the entire problem. But what you can do is move that force to point B and then add a special compensating couple moment. And this new combination, the force at B plus that couple, has the exact same effect on the object as the original force back at A. And by doing this over and over again, engineers can take a ridiculously complex web of forces and moments acting all over a body and boil it all down to just two things at one single point. One resultant force that tells you the net push or pull, and one resultant couple moment that tells you the net twist. It literally turns chaos into clarity. So what happens when we push this idea of simplification as far as it can possibly go, especially in 3D space? Well, we end up with something that has a very, very fitting name. It's called a wrench. And check out the key phrase here. The force and the couple moment are collinear. That means they act along the exact same line. It's literally what you do with a screwdriver or a wrench. You push forward and you twist, both along the same axis. That single combined push and twist action is the wrench. And it turns out that any super complex 3D force system can be boiled down to that one simple, elegant action. So let's just quickly recap the big ideas here. Number one, couples create pure rotation, just a twist, with no net push or pull. Number two, the moment of a couple is a free vector, which means its turning effect is the same no matter where on the object you put it. And finally, number three, that free vector property is what makes couples an absolutely essential tool for simplifying complicated, real-world engineering problems. So now that you know the secret of the couple, this idea of a perfect, pure twist, start looking around you. Seriously, whether you're opening a jar, turning a key in a lock, or twisting a doorknob, where else can you spot these invisible forces of pure rotation at work? Once you start looking for them, you'll realize they are everywhere.